Okay, so I'm working on a project that's a collaboration between the Department of Environment and Geography and the Department of Electronic Engineering. Quite often you get different interests from different sciences, and one science discipline will be able to enhance the other. And that's what we're doing here. So Sue mentioned earlier about problems with pollution. So there's lots of talk in the media, news broadcasts, things like that, about plastic pollution. It's big, it's loud, you can see it. So people get a good understanding of actually what's being talked about. But it's not the only type of pollution that's of interest. There's lots of different types of pollution, and lots of these pollutions lead into our ecosystem services, so the things that humans depend on. Okay, so we need plant production, we need nutrient cycling, climate regulation, all these things are fed in. Most of the ecosystem services that humans depend on derive from soils, and earthworms are very good ecosystem engineers. Okay, so they provide the soil, they generate the soil, they transfer nutrients from the soils to enable different habitats, other organisms, biodiversity, those kind of things. As well as that, they are also exceptional indicators of what's going on. Okay, so soil scientists study earthworms to actually interpret what's happening within the environment, what's happening with the soils. Yeah? Introduction of different chemicals, pollutants, pesticides, they all need to be monitored. So if we introduce a new pesticide, what's the effect? How does it affect the environment? How does it affect other organisms? Okay? Soil scientists need to study them. However, there's a massive problem when we come to study earthworms. Okay? They live in an optically dense environment, i.e. to you and me, they live in the soil and we can't see them. So that poses a big problem for the soil scientists. They'll start with an experiment where they put some earthworms in the soil. They'll leave that for a duration of maybe weeks, days, months, and they might add different pesticides. And they need to monitor what's happening. But it's not until the end of the experiment that they actually know if the earthworm's dead or alive. Okay? They can't see what's going on in the soil. So it's a big problem. More importantly, in the case of the dead worms, they don't know when the worm died. Okay? So some of these experiments might run for 5-6 months. That worm could have died on day one when you didn't actually have the pesticide that you were trying to investigate. Okay? Or it could have died the day before you did the experiment. It might not have died anything to do with the pesticide. It's really difficult to understand. So what my project, or the project I'm working on, hopes to do is to try and develop a tool or a system that will enable the soil scientists to monitor activity of earthworms. So therefore, day one, they can see the earthworms alive. After a week, when they've added some pesticide, the earthworm's still alive, it's still moving around, so things are still good. Week 6, there's no earthworm activity. So is it that concentration of that pesticide that has caused the death of the worm? Okay, it's that sort of thing. What we then want to do is hopefully be able to actually track an earthworm. So it's one thing knowing whether it's still alive or not, but we'd be interested to see how it's moving within the soil. Okay, so we can put biogradients in, different chemicals within different areas of the soil. Do the worms actively avoid them? Are they actively looking out for food? Are they avoiding concentrations within the soil where the pesticides, for argument's sake, are high? And I'm hoping to do that using sort of acoustics. All right, so my background is in the development of bespoke acoustic sensing systems, and I'm bringing my knowledge to this project in the development of these sensors. So I'm looking at sort of 3 different types of cheap, cost-effective sensors. Remember, these things we want to be able to use in lab environments. They're going to be dirty, they're going to get wet, so we need them to be cheap and reliable and robust. Okay. Ultimately, we want to be able to use them out in the field. So for field surveys, to monitor maybe say like a floodplain or something like that. So we need them to be cost-effective and reliable. Okay. So the type of sensors I'm using are piezoelectric discs. So they're the sorts of things that you get in the cheap birthday cards that your mum buys you, and you open it. So they're normally used for producing sound, but actually if you flick them, you get an input from them. So if an earthworm moves through the soil, the vibrations can be picked up by the piezoelectric sensors. So these things are cheap, they're pence. Okay, so that's one good thing. Piezo discs are only one direction though, so it'll only give you a good indication if the sound source is actually going directly towards it. If it's in the same plane, you won't pick anything up. So we're also using 3-axis accelerometers. So these are the types of devices that are in your mobile phones. So when you take a picture of somebody, you flip it round, it flips the image for you. So it can detect orientation. Likewise, it can detect the direction that a sound is coming from. So a sound wave hits it, we should be able to work out where that sound has come from. Okay. We did use some vibration sensors. They're effectively a spring on a wire. So they work really well if you don't want to detect an elephant crossing the savannah, but they are no good for worms. Okay. Now, the other big problem I have is anybody that's dropped a mobile phone in the toilet will know electronics and water do not mix. Okay. So I've got to protect the electronics somehow, and that's the biggest challenge, because in encapsulating or protecting the sensors, we detract the sensitivity of it, we reduce the sensitivity. Okay, so the accelerometers work on basically a moving mass. If we encapsulate it in resin as shown on there, we've added to the mass of that sensor, so it becomes less sensitive. So that's one of the challenges we face. Okay. Single sensors will allow us to detect just the activity. Okay, so on, what do we do with the laser pointer? On the top trace, this is an example of a typical experimental setup. So we've got 2 tanks. One tank will contain some earthworms and the sensors, and the other tank has no earthworms in them. Now we need that because we're picking up sort of vibrations and sound. There's lots of environmental noise. These examples were used in an anechoic chamber, but in the real world there's going to be lots of other sounds in there. The control will pick up the sounds from the environment. The subject tank will pick up the sounds from the environment and the earthworms, but we can be able to subtract one from the other, so we end up with just the subject. So these are examples. So we've got piezoelectric discs there and the results from the accelerometers. The thing to note is the accelerometers are very noisy in comparison, but we do get a much higher sensitivity from them. Okay, so the accelerometers appear at the moment to be working much better than the piezo discs. Okay, might be because we're looking at 3 axes, so we're picking up more directionality. Those are things we're looking at. Okay. The idea then is to take the single sensors, and build them into what we call stacked probes. So we put in multiple individual sensors into a probe. You can see the sort of concept there. You can see the kind of scale working out. So the top ones, that's the accelerometer you saw earlier in a different sort of potted version. So the mass is much smaller, so it's more sensitive. We can put that into a probe. These are the piezo discs. And then we can put the probes into the soil with a microcontroller. That's going to record the data from all the sensors, and it's then going to transmit it into a network of probes. So we can build a network of probes. That then allows us to triangulate the position of the worm. Okay, so we can use the time of arrival of the sound source, work backwards, and hopefully be able to create a track of where the worm's going. So we should then be able to monitor how it's moving through the soil. Is it actively avoiding areas where there's pesticide? Is it not bothered? Does it plough through it and go straight to the food source? Things like that. Okay, so we use that by a technique called multilateration. So effectively what we do is we take any two, take any 2 points. So this would be sensor 1 and sensor 2, and we can look at the time that the sound arrives at that sensor. We can then look at the difference between them, and we can work out which sensor the worm is nearer to. So it's nearer to one sensor because the sound arrived there earlier. Okay, so that gives us position. If we start doing that for all the pairs, then effectively we can build up a tracking point. So it's a little bit like how your mobile phone works. Again, phone analogy. As you're wandering around, it's sending out and receiving a signal from a transmitter. It uses the time difference between each of the transmitters to triangulate your position. Okay. So where are we at? Okay, so at the moment we've built the single sensors, both the accelerometers and the piezo discs, and we've done some initial tests with those, as you've seen. So early indications show that they are sensitive to pick up the worms within the small tanks. The idea is eventually to make these into bigger mesocosms so we can find them. We've developed the stacked probes, but as yet we haven't tested them. So that's going to happen within the next few weeks. We're actually going to be building some bigger tanks to put the probes in and start sort of trying to work out if we can actually track them. Then got to evaluate and optimize the tracking. So if I knew the time the worm made the sound, my problem is trivial. okay, because I can then say, right, it made a sound then, I've got arrivals this time, this time, this time, so it becomes quite easy, yeah? But I don't know the time that that worm made a sound, okay? So it actually becomes quite a big problem. And the way we solve it is we look at every point in the space and basically track backwards, and we do probability. So the best fit for all of that data is where the worm is, and that gives us a good indication of where it is. So we need to optimize. I need to optimize that. Okay. We're investigating the earthworm movements using the experiments. So far, with 2 species, we know that they've got different activity periods. Okay. That might be down to the size of the worm. So bigger worms might need to feed more often or less often. Okay. Small worms might feed sort of less infrequently or something like that. But those are the sorts of things that the soil scientists and ecologists want to know, because they don't know what's going on in the soil. They've got no idea. They know that a worm came to the top, grabbed a bit of food and went down, but they don't know really what it's doing with it. So we're helping solve some of those problems. And then sort of shortly after we've got some results back, we need to optimize this system, and can we scale it up? Can we then make it bigger to go out onto a field site? Can we monitor a floodplain, for argument's sake, with multiple networks? Yeah? So we've got one network, but there's no reason why we can't expand this out into sort of multiple networks that are linked together. Okay, that's everything. Thank you. Yeah.